Swayam Prabha. Digital India. Educated India.
Hello everyone, I'm Dakshi and today's lecture will be presented by Dr. Venkatakrishnan P. He is an Associate Professor at IIT Madras and a member of the Canadian Society of Chemistry. He got his PhD from IIT Kanpur and his research interests include molecular switches and sensors, organic electronics, synthetic chemistry and photochemistry. We are excited to have you here with us.
So, very good morning to all of you. So, I am from organic chemistry background, okay. So, that's a part of chemistry as you all may be aware. So, who are all here? From which standard to which standard? Everyone is 11th to 12th. Okay, it's fine. So, today what I plan to do is to talk about photo switches. Because we make organic molecules in the laboratory and we make them function. We tell them to do a specific work. I thought I would share my experience with such organic molecules with you. So the term photo switch as such gives you some kind of an indication. What do you think that it would be? When light is shown on, right? So that's what exactly we are going to talk about. So when you shine light on a particular molecule, it can do various activities, not from the ground state, because light phenomena always gives energy to the molecule and the molecule is in the excited state now, right? So from the excited state, many activities it can do because it is excited, right? So, but you can ask it to do a particular function. Either you can ask the molecule to change its color depending on, the light wavelength that you shine on it. So you can also ask it to do various other activities. It can change its geometry altogether and hence bring in a big change in the structure. So which means you are changing the volume as well. It's a huge expansion is going to happen. And as a result, some of them would swell, they can shrink. So all these kind of changes one can bring in by just shining light. As we move along, we'll also talk about few other properties that a light can bring in to the molecule, and you will understand it better, I believe. Any point, anywhere you have some doubt, you can stop me. Okay. So today, the objective is very clear. We are going to talk about some organic systems which would undergo a color change. Okay. And the color change is going to be reversible because for certain applications, then it would make a lot of sense if you have a reversibility that is put into the molecule. And certainly you are going to use light. And in the beginning of the title, you have organic molecules. That means you are going to deal with organic molecules. Okay. So organic molecules are composed of carbon, hydrogen, oxygen, nitrogen, sulfur, right? These are all the common atoms that you come across in organic molecules. And they're all connected by bonds. We'll talk about the nature of bonds. When you shine light onto the bonds, what happens to those bonds, right? And the resulting color change out of it. How does the color come from a molecule? What could be the primary reason for it, right? And how can you make it switch from a colorless form to a colored form? Moment you switch off the light, they should come back from a colored state to a colorless state. So you define the states, you define color, right? So many things are coming into picture. We start with very simple basics. Moment we say light, we should be aware of what light is composed of and what are the typical region that one should be worried about. So when we say light, immediately what strikes you is the electromagnetic radiation. It's a huge window As you see, if you want to represent it in frequencies, it comes from 10 to the power minus 21 to all the way up to 10 to the power 6 or 7, right? That much hertz, you will see a big window, okay? And as this picture tells you that the high energy radiations, frequency is directly proportional to energy, right? So when you talk about high energy radiations, these cosmic rays, gamma rays, X-rays, all of them are topping the list, right? And then comes ultraviolet radiation, and then comes the visible radiation. Lower than this, you have infrared, you have microwave and radio wave. So we are not going to discuss any of this because that's going to be very high energy. If you impinge them onto any of the molecules, that's going to supply a lot of energy to the molecule, ultimately destroying the molecule, because it's going to ultimately cleave the bonds. And the bond energies that you typically see in any organic molecules, the values, the energy associated with the bonds are quite higher actually, right? So these radiations are very high in energy, greater than that of the bond dissociation energy. So if you shine them, you will certainly see these molecules are gone into pieces, okay? So that is a destructive way of doing things. So we don't worry about any of that. But what you will see is in this presentation mainly about ultraviolet and the visible light, okay? In this particular region, in this electromagnetic region of the spectrum, right? What you will deal with, the ones that are higher, what we said, is going to cleave the bonds. So bond strength is much lower than that of that, and hence when you bring in such high energy radiation, it's going to cleave all the bonds. So that's not going to be productive. When you talk about ultraviolet and visible, this region is so perfect for the electronic transitions to happen in a molecule. It means you are not destroying the bonds, but you will facilitate electronic transitions. Where are these electrons in a molecule? In bonds. What kind of bonds could it be? Sigma, pi, and all that kind of bonds, right? Non-bonding electrons, whatever. So all of this is where these electrons are located. So when you shine this ultraviolet or the visible light region of the wavelength, then the the electrons that are involved in bonds are going to be absorbing, and they are going to undergo transitions. Transitions means excitations. Excitation means from a lower energy orbital to a higher energy orbital, they are going to jump. Because of that, you will bring in structural changes to the molecule. Structural changes in the ground state is different from that of the excited state, and hence you will see a lot of phenomena happening from the excited state. Okay, we'll talk about that later. So this is the particular region which will facilitate electronic transitions, correct? So in electronic transitions, you are not going to destroy the bonds, only the electrons are targeted in the molecule. That you should take. Then we'll move on to infrared, which is certainly supposed to be of lower in energy when compared to that of the UV and visible. So infrared region again is a huge range. If I have to represent in terms of nanometers, it starts from 750 nanometers and above, as you see, beyond visible, right? Can go up to 1500 nanometers, which you call it as near infrared region. Infrared region split into 3 regions, okay? So up to 1500 nanometers, it is called as a near infrared region. And from 1500 to 5500 or so, you call it as a mid infrared region. And you talk from 5500 to all the way up to 10 lakh nanometers, okay? That huge range is called the far infrared region. For any kind of structural characterization, you want to look at certain aspects of the structure. We will be more focusing on to the near infrared and the mid infrared region. Mid-infrared region, if you have to be frank, to some extent, up to say 4,000 centimeter inverse or so, not more than that. So such is the range that is very useful for us. Okay, what happens in this region to the molecule? Any compound, organic compound you take or inorganic compound you take. What happens in this region is electrons are not affected, electrons are not undergoing excitation. But what are the other motions that these molecules undergo? What kind of motions that these molecules can exhibit? These bonds, for example. Vibrations. They would stretch, right? They would bend from the plane. In plane, they could stretch. Out of plane, they could stretch. Out of plane, they could bend, right? And all these motions can happen within the molecule. It's actually happening now in your body system and in my body system, in surrounding, in the atmosphere. Everywhere these molecules are bumping into each other, right? Because they acquire energy from thermal means, thermal environment. The temperature that is available, it captures that and then undergoes this vibration. Thermal energy that the molecules get is nothing but the infrared radiations. Okay? So they acquire energy and they bring in kinetic energy to it. They go, right? Hit each other. But in that, while doing so, they acquire energy as well from the other molecules. They float around. And every molecule does this job of vibration, right? So if you want to study the vibrational motions of a particular molecule, then you should be targeting only the near infrared region to the mid infrared region to some extent. That will give you exact information about the modes of vibration that it can take up. What are the modes we said? Stretching and bending. Stretching could be again symmetric and anti-symmetric stretching modes. Symmetric and anti-symmetric stretching modes, if you have to visualize, let's say you have 3 atoms put together, right, in this fashion. Imagine that a symmetric stretching would bring in the extreme 2 atoms in the same manner, close to the central atom, and they depart away in a similar fashion. This is a very symmetric stretching. Anti-symmetric stretching could also be happening for the molecule. A way that one of the atoms at the termini would come approaching, whereas the other one would be going away. So this kind of an anti-symmetric stretching can also be noticed for a triatom. Okay. So such kind of stretching modes are very, very observable in this particular region, which is the near infrared to mid infrared region. So this region talks about only vibrations, molecular vibrations. There's another aspect that these molecules do, which is rotation, right? If you want to look at the rotational aspects of any molecule, you would target the microwave region, which is much, much lower in energy. Then vibrational motions are not activated in the molecule. You are not studying the vibrational motions. You are not looking at perspective. But the energy that corresponds to that of only the rotations are looked at when you shine in microwaves. Okay. So this is a whole set of activities that the molecules do in a normal scenario. But we will be talking about this particular region because we are more focused on electronic excitations and see how can you make these molecules do some work, function. Okay. So this is a very simple, very general idea about how you connect the energy to frequency and how you connect the energy to wavelength. You know, energy and the wavelengths are inversely proportional and frequency is directly proportional. And the message that you take is, if you convert the wavelength to, you can also convert that to wave numbers, which is also directly proportional to the energy. So I can bring in nanometers term in terms of wavelength. I can also bring in terms relevant to centimeter inverse for wave number, right? Or I can bring in hertz for the frequency. You shouldn't be confused. Okay. Well, so what happens actually for the electronic excitation to happen in a particular compound? So the setup is quite simple like this. This part you may be familiar, right? You shine in the white light onto a prism. There is a diffraction. So all the colors are split. Who did this experiment? Newton, right? So Newton studied this and he formed a circular one, which is called as a color wheel, and you would have studied all of that. So now, let's say you split all these colors out of a prism, and if you pass this into a solution which has an organic compound, right? And obviously organic compound or any other compound in the solution absorbs a particular wavelength, correct? And it lets the remaining wavelength out of the solution. So you capture the wavelength that is transmitted out, right? And you get a spectrum like this, which gives us an information as to what is the particular wavelength that is absorbed by the molecule. You look at actually the transmittance. You capture the transmittance, convert it into absorbance because they're inversely proportional. You'll be able to do that by this program, which ultimately plots the absorbance. In the x-axis, you will see either frequency or wavelength. Chemists got used to wavelength, so we plot with wavelength. Doesn't matter. So what you see is this kind of a spectrum. Some part of the molecule absorbs the corresponding wavelength. Now, this picture gives you a quick indication of some of the, this will not work here, yeah. So you have this blue light being absorbed, and you also see the yellow light being absorbed, and the rest of the wavelengths are let out, and the resulting spectrum gives you some kind of an indication as to what are the wavelengths that are being absorbed, correct? There are certain laws in this processes. Okay, there are two great scientists who talked about how this absorption that is being plotted, okay, will depend on the concentration and also the path length. So he gave a very simple explanation, and they gave this equation as a result. Absorbance is directly proportional to the path length. Absorption is also directly proportional to the concentration. What it means basically, could you visualize anything from this equation? Can you guess what it means? L means the path length. Path length means the light, right, travels into the solution. So the path is defined. So path length, if you alter, what happens? Path length is shorter, then what happens? Path length is longer, absorption is higher, right? Why? When the light passes through the solution, it will encounter many organic molecules or many molecules on its path. And as a result, many of the molecules would absorb the light of particular wavelength, and hence the absorption should be proportionately high, right? And how about the concentration? Again, right? More concentration, more number of molecules in the solution. Again, it will face the light very effectively because many molecules are floating around, many molecules will absorb the light, and the absorption would increase. Okay, so these two are the crucial parameters in the experiment. Whenever you plan an experiment, you have to be very much careful about deciding the concentration, and you have to ensure the path length is sufficient enough so that you get reasonably good absorption, which you can see and get. Okay, there are limitations which I don't want to go into, but then it's fine for you to take this message. Molar absorptivity, that is denoted here as an epsilon, it is a constant. Okay, it is constant for a particular molecule. So it is a characteristic property of a molecule. Either I record the absorption spectrum at IIT Chennai, or someone records in Caltech for the same molecule, the molar extinction coefficient should be same. Okay, it's a very unique property for a molecule. So if somebody synthesizes the same molecule that I had synthesized here, and I had reported the molar extinction coefficient, one would be able to synthesize the same molecule in any part of the world, right? So when they do it, they can estimate the molar extinction coefficient to cross-check if he or she had actually synthesized the same molecule. It's a quick verification. It's a characteristic property of a molecule. What it denotes, if the molar extinction coefficient number is so huge, say 10 or 20 or 30,000 or probably a lakh or so, right? What it denotes is the intensity of absorption for that particular compound is quite high. When I say intensity of absorption is high, that means the probability that the electrons are undergoing transitions are also high. Correct? So that is what this terminology means, molar extinction coefficient. So it is the probability of electronic transitions which would represent in terms of the intensity, and you will be able to say, okay, it's a very good dye because even in a very low concentration, I am able to get a huge absorption of higher intensities. Yeah. The sample cuvette that you have, because this is where your sample is put in, right? So the light travels within this time, within this length. Then how much molecule it encounters? Obviously, outside this sample vial, you don't have any of the your molecules. Your sample is not present. So path length is from this end, from the light is hitting, width of the tube, sample tube, in other words. It is the width of the sample tube. Okay. It's not L now, it's I0. So absorption is denoted as the light that is incidenting onto the solution, before incidence and after incidence. I0 is having composed of all the wavelengths now. So it is the intensity of light. Few wavelengths are absorbed by the sample. Remaining is let out. So that's going to be I. If the ratio of these two are measured, you know what are the wavelengths that are absorbed. Right? So that is what is denoted by I0 is the incident light. I is the light that is transmitted out of the solution. Before absorption. Okay, so this is a simple cartoonic picture for you. The light composed of these wavelengths hitting a solution. Some wavelengths are absorbed, remaining is let out, and the resultant color is seen by the eye. So what we are actually seeing is the transmitted light. Right? The color that I am having in my t-shirt is blue. Doesn't mean that this is the blue color that the dye which is quoted here is absorbed. No. It is going to be a different wavelength, right, than what you see. So complementary color is what we see, what we perceive. Okay. So let's look at the correlation. This is a nice correlation you can make from Newton's circle color wave. So what it clearly indicates is, for example, if a visible color is red, if you are visualizing a red color, that means it must have absorbed a bluish green color. And thereby you know what is the typical wavelength range that these dyes would have absorbed. Okay, what are the wavelengths that it would have absorbed? It spans from 490 to 500 nanometers. Which means it has absorbed this greenish blue color, and because of that what you see is the orange color. Okay. And similarly, if the color that you see is green, right, the absorbed color is actually red, and which means you have absorbed a wavelength of between 650 to 780 nanometers. You can see that the absorbed color is red. That means the absorption is happening somewhere close to the near infrared region. Already you have gone there. Okay. So this is a nice correlation between the absorbed color and the complementary color. And the color that we perceive gives you some kind of an information about the absorbed color, and thereby you can go back and look at the wavelengths. You know what are the wavelengths that could have absorbed by this sample. It's a nice correlation. Yeah.
So this is for all the colors. Suppose we are seeing white on your t-shirt, for example. So what will that correlate to? White itself?
No. White means it's a combination of or, G and B, all the colors. If you have or, G and B, mix all of them in equal proportions, 0.33, 0.33, 0.33. The resultant color that you must see is white. Let me put it the other way. Let's say you have you mixed the color that comes out as red and blue and green. You combine all the three, the color that you see is white. So then absorbed color should be different. That should be black. Okay. So what you see, absorption is a different phenomena when compared to that of the emission. Right. Two complementary colors when you combine. Let me put it in the other way. Let's say you take two complementary colors. You have the two opposite colors. Let's say red and green. They are complementary to each other. Because absorbed color is red means you will see green. Right. So they are complementary to each other. You mix these two, you should be able to produce white light. Yeah, this light should have all the components. White light should have all the colors, right? That's how the prism experiment was done. So the white light should be composed of all the wavelengths. Then it is split. You have all the colors in them. Black, yes, when you start the absorption, if you record the absorption spectrum for the black colored compound or the sample, you will see absorption all over. All the wavelengths are absorbed. But white color is an emission that comes out of the sample. Okay. So you will have two different processes, but right now we will not talk about emission. We'll talk about only absorption. Yeah.
Sir, so can this table be reversed? So in the table you can see you have blue. If you absorb bluish green, you get red. And if you absorb red, you get a blue green.
Yeah.
But for example, for the violet, you absorb violet, you get a yellow green. So if you absorb a yellow green, why are we getting purple? Why don't we get violet?
If you are absorbing green, then you get red purple. So the color change in the green and the yellow green is very minor. You will take this whole region, let us say 500 to 595. You already split that into two. What you have is if the absorbed color is yellow green, you are seeing it as a purple. Red, purple or magenta, whatever you call, they are very close in the region. So you see the transition here, right? From the violet to magenta and red, it passes through red. So this region belongs to 500 to 595. So 500 to 595, this is the region. Where you are exactly putting your wavelength is something different. So I don't see a big difference between these two, green and yellow. Yellow purely you will be able to see, but greenish yellow, green, yellow, right? So color coordinates wise, if you see, there are small differences between them.
Sir, so if let's say I absorb some specific X nanometers, and because of that I see some other Y nanometers. If I absorb Y nanometers, will I see X nanometers?
Yes.
So it's like
they are complementary.
Sir, but here
these two are complementary to each other.
Sir, but here if I absorb yellow green, I see purple. But yeah, if I absorb violet, I'm getting yellow green. Shouldn't it be I absorb purple to get yellow green?
You should be absorbing purple to get yellow green. Then it should be appearing.
Yes, sir, but it's written violet, yellow green, the last one. Violet gets yellow green.
Yeah. What it means is, if you go further into blue plus purple, let us say, so make it purple, then you will end up in getting probably green. Okay, so the extremes are merged to some extent. Okay, don't go by the absolute numbers here, but you have a feel as to how this is complementary to each other. Okay, yeah. Here I'm showing you the sample's absorption spectrum. It won't, because it doesn't have any absorption after 350 or so, right? So any sample you have, you can record the usable absorption spectrum to know the range in which it absorbs. Then you decide what is the right wavelength to be shown on this sample. Now what are the wavelengths that you can shine? Any wavelength in this span, you should be able to shine on the sample. The color is going to be same, whatever you see. Okay. So within this window, whatever the molecule that it can absorb, it is absorbing actually. Any wavelength you shine in, it absorbs. The resultant color is going to be same. Intensities could be different. Why? You see a shape in that, right? If you want to see a better intensity, then you should be, or better absorption in other words, You must excite it in this particular wavelength which has a maximum. So it is the molecular characteristic feature. In this particular wavelength, this molecule absorbs to the maximum. So you choose that particular wavelength. Any studies you want to do, record the absorption spectrum, decide on the wavelength and shine on the sample. Then you can look at their properties. Because that is the wavelength you know that has major epsilon, molar extinction coefficient, or the intensity or the absorbance. So you are 100% sure that the compound, you are not going to miss it out. You cannot be choosing any wavelength beyond this. Molecule doesn't absorb. You may be shining, but you will not see any of the property that it gives. This molecule doesn't absorb. Okay, it's different. Yeah. So you have to report the molar extinction coefficient always within the brackets, the corresponding wavelength at which it is measured. It is dependent. Yeah, it's not. It is dependent on the solvent. It is dependent on the wavelength. Okay.
So, sir.
Yeah.
Sir.
Somebody else. Yeah.
Sir, do you think black is a color, or do you think it's an absence of color?
Black is a combination of colors.
Combination of colors,
Yeah.
not absence of colors.
No absence of color.
Sir, so let's say we have a compound whose absorption has been studied already, and we find that it absorbs, let's say, red color. With the highest absorption is for red color.
Okay.
So that is with when we are shining white light, we see the complement of red color. So now if we shine that exact same red color on it, won't it appear like a very, very, very dark red or a complete black? Like fully opaque.
It will still be red.
Sir, but then you're sending the exact light which is absorbing. There's no other light which is
No,
sending.
you are exciting the sample with the wavelength in which it actually absorbs right? It absorbs the light, but already you are perceiving is the same because it exhibits the absorption, the whole set of wavelengths. It doesn't have a spike, right? It has a whole range of absorption. Any wavelength you shine in within that range, it is going to absorb. So that's why the range is mentioned. Whenever you see the absorbed color, there is a set of wavelengths, range that is mentioned. Okay. So the perceived color, if it is red, which means you know what is the absorbance range in which the compound maximum has probably. Some of the portions it will have very minimum.
Sir,
Okay.
sir, but that's when you have different colors. So it can only, sir, for example, in the diagram which you've shown, the previous one. Yes, sir. Over here, you're shining all different kinds of wavelengths.
Right.
And it's absorbing some of them and letting some of them go through. So now we find out which ones it's absorbing and we find which one it absorbs the most.
Right.
Let's say 90% absorption. So now we take that wavelength of light and shine only that wavelength of light through the solution. Won't it be like that very, very dark color or black?
It will absorb.
Yes, sir, but there's nothing else left.
Nothing else you will do.
So it'll be black.
It will be in the same color. What it means is it absorbs that wavelength. You have absorbed these two wavelengths. You are seeing let's say you have red color, and what you are seeing is a red color. Okay, but the wavelength, set of wavelengths it is absorbing is different from that of the color that you are actually perceiving. So any wavelength you choose in that wavelength, whichever it has absorbed, then you will still see the same color. Because it's already absorbing those only. Is it clear or not?
So if we absorb, if we make a sample that absorbs all the visible light, we would see black, right, at the end, the color that we see coming out would be black, right?
Right.
Yes, sir. So as he said, if we point out, example, if the solution absorbs all red, and if we pass only red light, so in that case again we would see black, right? Why do we see the same color?
No. If you are seeing a certain color, there are certain wavelengths that are being absorbed by that.
Yes, sir.
Correct. And that is why it gives you this color. Now, the absorption spectrum gives you an information as to what are the wavelengths that the sample absorbs.
Yes, sir.
Right? You shine in light of that particular wavelength. It should show you the same color. Why do you think that it's going to be different?
So same color as in which same color where?
No, this is the whole range that this molecule absorbs. Let us say the sample in the vial has absorbed these wavelengths, starting from 100 nanometers or 180 nanometers to 350 nanometers. You shine any light beyond that, say 400, 500, 600 nanometers, the molecule is not absorbing actually.
Okay.
But what are the wavelength it absorbs? It absorbs only up to 350 nanometers or so. Any wavelength you shine onto it, it is going to absorb. You will know what are the wavelengths it can absorb by recording an absorption spectrum. But it doesn't change the color. We are not talking about switching of color yet. We are just talking of the origin of color.
So now let's say there's a room, the lights are on, I can see because the lights are coming to my eyes now. Now if I switch off the tube light, there is no light. So I see black, right? Now there is nothing entering in my eyes, but I can see black. What do you think of that?
What do you mean means when you switch off the light,
Yes. There is no color.
These objects do not have particular wavelengths
Yes.
to absorb.
Yes. So it's black.
So it is black.
So it's not exactly a color.
It is not black. You are seeing it as black. Right? No, but its actual color is as such.
Yeah.
Right? So you are not able to see the color. That's a different story. But why it is you are not able to see the color?
Because there's no
Because
light.
there is no light
Yes.
that it can absorb.
So if there is no light, you perceive it as black, basically, right? Okay.
But your eyes have a tendency to look at even in a dim light.
Yeah.
That's
I mean,
because of
no
the
light at all.
yeah,
That's
that's
what I'm
because
saying.
of the vision process that is happening within our rod cells and cone cells in the eyes. Okay, so we spent a long time here. Anyway, it's good. So various colors, right? Many natural dyes can have absorption at certain different wavelengths. As you are seeing here, for chlorophyll, it has absorption in the near infrared. It also has absorption in the ultraviolet region and also in the visible region. Ultraviolet region is less than 400 nanometers. So you have a weak absorption, and then majority of it is in the visible region. All of them are colored, so you must see absorption in the visible region. If somebody is, or you are not able to see the color, that means its absorption is happening in the ultraviolet region probably. You are not able to see the color of it. Moment you see the color, you must realize that it is absorbing in the visible region. So absorption for this compound is in the visible region. So all of these have dyes within themselves, organic molecules. So their absorption is most of them have absorption, majority of the absorption after 400 nanometers. And till 700 or 750 nanometers, the whole visible range, these dyes absorb. Okay. Well, because the molecules are huge there, you may have a bigger sized particles because of their competing associations between the molecules or favorable interactions between the molecules. So you will bring in that more and more into the solution. So they would tend to scatter light. So you are not actually calculating only the absorption phenomena. No, because you also have other competing processes initiated. So concentration is a very, very important thing when you are recording the absorption spectrum. Usually, for your information, we used to deal with 10 to the power minus 3 molar solution to 10 to the power minus 5 molar solutions. Okay. Minus 6 is even better because you are really separating the molecules in the solution. Okay. You are reducing the intermolecular interactions in solution. So typically this is the concentration range you would deal with. You may play with the concentration depending on its molar extinction coefficient also, right? If you start with 10 to the power minus 5 molar solution, you record the absorption spectrum, you find it's very weak. The signals are very noisy. Then probably you may want to decide it to increase the concentration. So from 10 to the power minus 5 to 10 to the power minus 4, if it's still not better, go up to 10 to the power minus 3, you will be able to have certainly a reasonably explainable or understandable absorption spectrum. You can increase the path length to make it better. That's also true. Okay, but for that you need to have the cuvettes of different volumes and so on. So that's quite difficult because making a cuvette itself is challenging because we always go for quartz cuvettes. Because why quartz? Quartz is transparent beyond the wavelength 250 nanometers. If you use a normal glass, it has an absorption up to 350 nanometers. Some of your organic compounds may absorb starting from 200 nanometers, right? So if glass absorbs till 350, you may lose an important information that the compound has to give you, right? So it would be wiser to choose a glass which is transparent starting from the ultraviolet region itself. So quartz gives you that flexibility. So we deal with quartz, so you need to make different size cuvettes of, perfect path length and so on. So it's quite laborious and it's very expensive also. Quartz, it's quite expensive. Okay. So one has to be careful in doing the experiments. That's experimental part of it. Anyway. Yeah. Beyond this, the region, infrared region. So you have sun spectrum starting from here, let us say all the way. And ultraviolet region below this, visible region from 400 to 780 or 700 nanometers. So what you have to have an information about the absorption. These are colored compounds, they absorb in the visible region. Okay. Fine. So absorption spectrum is usually broad. Okay. As we saw in the previous case, one of the examples, absorption spectrum were broad for organic molecules. When we say molecules, again they are a combination of atoms. Right? So if you look at the atomic absorption, for one atom you want to record an absorption, sodium ion, you want to record an absorption spectrum. They are going to be very sharp, unlike that of the absorption spectrum that you see for the molecules. Okay. The reason being that you have defined the energy levels there, only electronic energy levels, because those are atoms. You do not still hybridize them to make, molecules. So independent atoms, the energy levels are very defined. You have S, P, D and so on, right? So you have energy levels quite defined. Whenever you see a transition from a lower energy orbital to a higher energy orbital transition happens, S to P, for example, in the case of sodium. So you will see very sharp lines, right? Let us say you have two electronic transitions possible in an atom, you will see two sharp lines. Only lines you will see as an absorption spectrum. And you can easily explain that one is at a longer wavelength, S0 to S1 should be associated with a lower energy, right? Longer wavelength, so energy is low. So the transition should be happening between the S0 level and the S1 level, associated with the lower energy. Then if you get another line, the one that you see at a higher wavelength, meaning that it is associated with a higher energy transition. So from S0 to S2, if an electron jumps, then that transition is associated with a higher energy, and that you would see it at a shorter wavelength or lower wavelength. Okay, so you'll be able to explain it very clearly for atomic absorptions. On the contrary, if you go for molecular absorptions, you combine atoms. So many bonds are established between the atoms. Then you have to take into account not only the electronic energy levels, but also the energy that is associated with vibrations and rotations. Right? So how are they placed in energy scenario? You have these electronic energy levels, let's say S0, S1, S2 are all electronic energy levels. Between the electronic energy levels, you have the vibration energy levels. Within the vibration energy levels, you have rotational energy levels. So their energies are distributed like this. Okay. So you have electronic energy levels here. These pink lines that are denoted as the vibrational energy levels. And within the pink lines, you have the small blue lines. Those are rotational energy levels. So you can calculate the energy difference, right? So between the rotational energy levels, if you take up the energies, are very, very small. That's why you need to have a microwave to do studies associated to rotational energy levels if you want to study that. Vibration energy levels are slightly more in energy. They are separated little farther. And these energy levels, the energy between them exactly matches with that of the near infrared and the mid infrared we talked about. And if you want to study these energy levels, then that would be the suitable wavelength region. Electronic energy levels, as we discussed, ultraviolet and visible radiations are very suitable. Now, in a real scenario, right, at this room temperature, these molecules are already undergoing vibrations. molecules are already undergoing rotations, right? They are doing already these processes. Now, if you shine in light onto these organic molecules, along with the electronic transitions, these molecules are populated at the rotation energy levels. Some of them are populated in the vibration energy levels because they are already acquiring energy. So, you see hundreds of molecules, 40 of them are in the electronic energy level, another 40 of them are in the vibration energy level, 20 of them are having that energy which corresponds to that of the rotation energy level or vibration energy level and so on. So, molecules are distributed in the ground state at slightly different levels. You pump in an energy which is associated to the electronic energy transition, particularly in the region from UV to visible. These molecules would get excited. So, they would excite from here, they would excite from here, they would excite from here. All of this is possible. So, you have a combination of electronic transitions, not exactly from S0 to S1 as you saw in the case of atomic absorption. Okay. So, this complex scenario is possibility of different transitions, and that is what you are seeing as a broad signals in the absorption. Okay. So, molecular phenomena involves rotations and vibrations. Along with the electronic transitions, molecules that are populated at a slightly higher energy level in rotations and vibration energy levels will also undergo transitions. So, you will have a combination of these absorptions happening at different energy levels. So, they are broader. Okay. But nevertheless, the peaks that you are getting, okay, you saw some peaks, you saw some trough and all that, right? This corresponds to that of the electronic transitions. So, if you know the wavelength of those peaks, you can directly estimate the electronic energy levels distance. How much are they separated from S0 to S1, right? S0 to S2, for example. All of them could be nicely calculated, and in principle, any wavelength you take from there, you will be able to deduce the corresponding energies associated with them. Okay. So, this is very useful information for you to decide upon any excitation phenomena, electronic excitation phenomena. This is just to give you a picture as to how fast an absorption could be in a system. Okay. Absorption processes are very, very, very fast, unimaginably fast. If you provide them the sufficient wavelength or energy, these molecules absorb in a time frame of about 10 to the power minus 15 seconds. A few femtoseconds, these electrons are promoted from the ground state energy levels to the higher energy levels, or lower energy state to the higher energy levels. It's very, very fast. And that process happens every now and then, everywhere, all around, surrounding us, and in any organic systems you take or any system you take, this phenomena is happening. It's a very fast process. So, absorption is the fastest process, you would say, right? Moment it reaches to the excited state, the electrons are pumped, geometrical changes are expected to happen on a molecule, because now the electron density distribution gets modified, right? Because initially it was equally distributed, you pump in an electron, the one that is weakly bound is going to be promoted quickly, and there is some electronic reorganization that is going to happen, and hence you can have structural changes associated with that process in the excited state. Okay. So, these changes are bound to happen, which means what? You are creating a reactive state. What is the time frame in which these structural changes can happen? 10 to the power minus 12 seconds. So, what happens during excitation? During excitation, when it absorbs and it goes to the excited state, means molecule doesn't even realize what has happened to itself. So, nuclei are in the same positions during the absorption process, right? Electrons are lighter than the nuclei, right? So, that will be quickly transferred to the excited state. The nuclei are still in its positions. It is excited, but it does not realize that it is in excited state. But within 10 to the power minus 12 seconds, these structural organizations would happen. So, there are different spectroscopic techniques, ultra-fast spectroscopy, right? Here some of the faculty members have, in physics have these spectroscopic techniques. You can study the molecules as to how they behave in the excited state. Okay, in 10 to the power minus 15 seconds, what happens to this molecule, you will be able to understand. So that is happening in 10 to minus 12 seconds. Okay, these structural changes. Then it relaxes. When it is being promoted, we saw in the previous slide, you can notice it here. Gets excited from S0, reaches to S1. Doesn't stop there exactly. It goes to slightly higher vibration energy levels of S1 as well. Right? There can be scenarios, it can be pumped to S2 as well. Right? So all of this happen and it has to now relax from these vibrational energy levels to S1. That time frame is 10 to the power minus 12. Once it has reached S0, let us say, then it has to come back to the ground state, losing the excess energy that it has acquired in the form of a force. Right? So when it comes to the ground state, what are the ways by which it can release the energy? One of the ways it can release the energy is by heat. Lets out, it's a waste heat from the molecule. Another process is that, okay, heat I mean by what? How can the molecule release the heat? What? Radiation. What kind of radiation could it be? Infrared radiation, which means you are talking in terms of this electronic energy acquired by the molecule is distributed into the bonds. Now it would start to vibrate. Right? And then rotate. All this process happen. This is what we call it as energy wastage as heat. Heat means you will not be able to feel, but you will be able to detect them. Right? But this electron excitation relaxes, structural changes come to the S1 and then it relaxes, vibration starts, right? Releases the energy into the bonds, collision, it is lost, comes to the ground state. Now when it comes to the ground state, right, when the form of heat we said, there is another competing process that can happen. Whatever the radiation it has absorbed, it can give it out in the form of light. This is another process. This you call it as emission. Absorption happens from the excited state, it can emit the energy, whatever it has absorbed, in the form of light. Okay. So these are the two processes by which a molecule can relax to the ground state. When a light emission happens, you will be able to detect them. And that is the relaxation process. There is a different spectroscopy which can tell you information about the emission, which is called otherwise as fluorescence. Right? Any light that you see, it is emitting actually. This is an emission. And TV screens, they give out light, different colors. So that's an emission. Right? Likewise, you will see emission phenomena around you. So that's an emission process. Now, when you have emission, there can be two types. It can come from directly from a state which it has reached. The state I don't know, you may be familiar about singlet and triplets. Electrons when they are paired, right? You call such states as singlet states. When electrons are parallel, the signs are they are same, they are not anti-parallel, they are parallel. Then you will call them as triplets. So for the triplets to happen, this is a more stable state. When the anti-parallel states, it is a more stable state. So energy wastage process can also induce them to flip the spin. We talked about bonds undergoing vibration. What happens to the spin? It can also undergo flip from anti-parallel to parallel. There is another competing process from the excited state for the molecule. When that spin flip happens, you call that as a triplet state, and from the triplet state also molecules can emit. That is called phosphorescence. Phosphorescent materials, phosphorescent compounds, right? Even you do not have light, you can switch them off, those will be still emitting. But fluorescence, moment you switch off the light, the emission is gone. Okay. So in the phosphorescence cases, even if you switch off because you shine light onto it already, switch off the light, they keep radiating. They keep emitting the light. That is called phosphorescence. Why such delay happens? Fluorescence, moment you switch off the light, it stops giving out the light, right? So it is very immediate. So which means that is emitting from the singlet state, right? Comes down. But on the other hand, triplet state involves a spin flip, right? So from here to here. So there is a time delay. That delay is up to few microseconds to milliseconds. Nowadays it is up to seconds. People have modified the molecules to reach up to seconds. So you switch off the light, they will be still emitting. And from the triplet state, how does it come to ground state? It has to be singlet. So again, spin flip has to happen. It has to come to the ground state. So two spin flips from singlet to triplet and from triplet to ground state, it has to accompany. So look at the delay that is associated with this process. And that's why moment you excite, they absorb the light. All this spin flip takes sufficient time. Even if you switch off the light, they would still be emitting. Such is called phosphorescence. Okay. So these are the competing processes in the electronic excitation. We will not talk about the emission. We will only talk about the absorption now. Okay. This is a simple absorption spectrum for this dye, a complicated dye, right? Very popular in solar cell applications. You have absorption, as you can see, peaking at 500 or 520. The blue curve that is shown on the other side is the emission spectrum of this dye. Emission, you find it always at a lower energy when compared to that of the absorption, because that is an energy losing process. Because from the excited state, it has to come down, associated with a lower energy. And that is why you see it from 500 to 750. And for this compound, fortunately, they are appearing as a mirror image, right? Left hand side is equal to the right hand side, right? So they are very similar. Nice pattern is shown. So this is absorption spectrum and emission spectrum. The thing that I want you to observe with this compound is the broadened absorption, because it's an organic molecule, combination of several atoms, and you are seeing all these along with the electronic energy levels. You also have the vibronic energy levels transition, right? All of that is there, and this significantly broad. They have not shown the absorption less than 200. There is absorption less than 300 also. Okay, so it is flat for some time and then it peaks up. Okay. So now you have seen that molecule. You would have identified the bonds that are present in that molecule, right? So you can typically have a sigma bond in any organic molecule. Organic molecules are composed of pi bonds. You also have heteroatoms present in them like nitrogen, oxygen, sulfur, and so on. They also have lone pairs of electrons associated with them. So electronic transition can happen from all these type of bonds involving electrons, right? So we saw sigma, pi, and n. If you want to put them in energy levels, they would appear like this. Sigma is of the strongest bond, right? So they have very low energy, very stable. Then comes the pi, then comes the non-bonding, and the pi sigmas associated antibonding orbitals. Antibonding orbitals are always of higher energy, as you know, and any electronic transition has to happen. It should be from the lower energy orbitals to the higher energy orbitals that are antibonding in nature. When we say lower energy bonding, lower energy orbitals means what? Bonding orbitals, which means they have electrons in them. Correct? They have electrons in them. From only then you can promote an electron from the lower energy level to the exit. So which means what? Any electronic transition has to be happening not from the pi star or sigma star, because they are vacant, right? Not from the higher energy, from the lower energy filled orbitals, you are going to have electronic transitions. Well, so the possibilities, if you have, yeah.
Suppose you have electrons, say in the 2p orbitals, on the 2p bonding orbitals, and then you don't have any electrons in the anti-bonding. So right now the molecule is diamagnetic. Say one electron goes from here and enters the unoccupied antibonding. Will that affect the paramagnetic? I mean, will it become paramagnetic then?
No,
It will not.
it is paired now.
Yeah.
When electronic transitions happen, it should happen like this only.
Okay. So when you add everything, you still get.
Yeah, it's not going to be paramagnetic. Paramagnetic should involve a spin flip. Excitation process will not involve a spin flip. Excitation process. From the excited state, then it can do the spin flip. Excitation process should not involve the spin flip. Okay? Excitation process, if it is parallel, I mean they are paired in an anti-parallel manner. The electron, the electrons are promoted now after absorption. So spin doesn't change, goes like this. From the excited state, right, depending on the environment, it would spin flip. That is one of the possibilities. Not always.
Sir, so again, let's take his example where there's a vacant p star orbital and there's the 2 electrons in the p orbital, and you excite one to the p star orbital. Doesn't that change the bond order of the molecule?
It will.
So the p bond will completely break because now there's no p bond, only the sigma.
But it is not a permanent change. You understand, no? We are not ionizing. Ionizing is completely removing an electron from the molecule. That would impair the bond permanently, right? But now it's an excitation. So electrons are promoted within the orbitals. You have the sigma, pi, antibonding, bonding. So from the bonding to the antibonding, nothing happens to the molecule. It relaxes, it comes back, right? But your point is very valid, okay? But it is a temporary change. It comes back. But people have studied very carefully the carbonyls particularly. Carbonyl is sp2 hybridized, right? This carbonyl carbon changes its hybridization in the excited state, sp2 to sp3. But that's a temporary one. So within the time scale, you will see the hybridization change. After that, it would reorganize itself, comes back to the ground state. Okay, so it's a temporary error. Your guess is correct. So electronic transition, if it happens, the possibilities are from the filled to the vacant, from the bonding to the anti-bonding. So the possible scenarios, for example, okay, you can think of sigma to sigma star. You can think of sigma to, pi to pi star. You can also think of n to pi star. You can also think of n to sigma star. For example, you can have such kind of transitions. Now, it depends on the molecule that you have. What is the kind of molecule that you deal with? I'm just summarizing you to give you a quick idea. So, you have, let us say, there's no typical functional groups here. Anyway, so if you have a saturated compound, means what? For example, alkanes. It has only carbon and hydrogens. It has only sigma bonds, right? Carbon-carbon sigma bond and carbon-hydrogen sigma bonds. So, given a scenario such as this, what is the kind of transition that is possible? Sigma to sigma star. That is the only transition that is possible for a saturated aliphatic compounds. So, where does this absorb? Sigma bonds. This molecule has only sigma bonds. It should be in the ultraviolet region. That means these compounds are typically colorless. Okay. So its absorption typically happens between 150 to 250 nanometers, ultraviolet region, or you may say far ultraviolet region, which is less than 200 nanometers. Can go up to 180 or so. Okay. So sigma to sigma star transition, molar excitation coefficients we talk about, they're fairly low. So you cannot estimate the molar excitation coefficient for those compounds. And if its absorption is less than 200 nanometers, believe me, you cannot conduct the experiments at the atmospheric conditions. Because oxygen competes. Oxygen's absorption is around that region, 190 or 185 or so. It's very difficult to measure absorption for such compounds. Okay. So what do? When you are measuring, if you want to measure such kind of compounds and you realize that oxygen is also absorbing, you can do it in vacuum. So that technique is called as vacuum ultraviolet absorption spectroscopy. It's a separate setup. You can do it in vacuum, or you would want to do it in a nitrogen atmosphere, whose absorption is not interfering at 185 or 180, but 165 or so. So you are safe in that region, right? So you surround your environment with nitrogen molecules, then you do the experiment, or as he suggested, you can create a vacuum and then do such experiments, okay, in a gaseous phase. There can be few functional groups that you can see in the organic chemistry. For example, we discussed about carbonyls. You can also think of alkenes, right? Carbon-carbon double bonds. You can also think of carbon-carbon triple bonds, alkynes. So you can have various scenarios, and these functional groups, because the molecule has, you will have pi to pi star transitions, particularly for alkenes and alkynes. When you talk about carbonyls, what are the electronic transitions possible? You can think of pi to pi star. Along with that, you will also have n to pi star, because non-bonded electrons are there associated with the oxygens, right? There are two non-bonding electrons. So here is a simple example. What is this molecule? It is formaldehyde. Very, very basic carbonyl compound. I am taking it for example. Now here, what are the electrons that you find? Sigma electrons you can find, sigma bonds, pi electrons you can find. You can also locate the non-bonding electrons very easily, right? So transitions possible are the transitions that are with sigma, from sigma, transitions that are from pi, transitions that are from n non-bonding electrons. Which one you think will be very easy? Non-bonding. Why? Because they are freely available. They don't have a commitment, right? They don't involve in bonding. They are freely available. So just use even a lower energy wavelength. Of course, lower energy I mean not when compared to, means lower than sigma, lower than pi, okay? So give such amount of energy, you can excite the non-bonding electrons. But we don't specifically do that. We give a range of wavelength and molecule absorbs, you will look at the phenomena of every states. So lower energy, the lowest energy involved electronic transition for this molecule is the n to pi star and n to sigma star. Both of them are possible. And then comes pi, right? Pi to pi star transitions you can encounter for this molecule. You can also think of sigma to sigma star. We said sigma to sigma star is often seen in the vacuum ultraviolet region or far ultraviolet region. So we cannot detect it in a normal scenario. So forget about it. So you will be then more having an options of looking at only pi star and n pi star. You are left with only these two, right? So these two transitions you will be able to detect starting from 200 nanometers to 400 nanometers or 500 nanometers or so. Huh? N to sigma star is possible. Why not? N to pi star into sigma star is possible. So it is a typical scenario, just showing with respect to the bonding scenario. So you have ethylene. Now you fill this because two sigma electrons are there, you fill it. Pi 2 electrons you can fill it. If you want to show the electronic transitions from pi to pi star, you can think of sigma to sigma star. But the lower energy transitions are pi to pi star. Okay. So you can, when you record the absorption spectrum, this is what you should look at. The transition that is corresponding to this peak, maximum, right? That should be corresponding to pi star transition. And for a typical ethylene, you will see the absorption happening at 165 nanometers. There is no flip and spin. It is, yeah, sorry. So it should not be, it shouldn't be like this. It should be like this. There should not be a spin flip during electronic transition. That is forbidden. It's not allowed. Okay. You will also look at the molar extinction coefficient. The molar extinction coefficient gives an indication that is a very strong transition, right? Absorption is, intensity is quite high for simple ethylene. So pi star transitions are often associated with a huge absorption. You will be able to detect them easily. That's what it means. Okay. simple experimental setup is like this. So you take a sample, put them in solution, right? Keep a sample here. You can keep a reference meaning no sample, but it will be with only the solvent which you are using to dissolve your compound. Okay, so it will be blank. In other words, you can call it as a blank without sample, and here you will have with sample. So from the white light source, the light beam is hit on both the samples. When it hits, it's I0. When it exits the sample, you have I. Certain wavelengths are absorbed, and the instrument does a job of taking the ratios of these two. Why you are taking a solvent here? Because it neglects the contribution played by the solvent, because it's being kept in both the sample vials. Okay, it subtracts that contribution, gives you the contribution corresponding to only your sample. Is that clear? So then the detector tallies all this, matches all these calculations, gives you a spectrum like this, absorption spectrum. Process is very, very fast. Okay, yeah.
At the beginning of the lecture, you had mentioned A is log of I by
I by I
naught.
Yeah.
Here is it I naught by I?
That must have been
Which one?
I by I naught.
I by I naught is right.
Right? So, incident light divided by the light. So, it should be I0 by I, not by I naught. Yeah, I0 by I. So, that was the mistake there. Okay. Good, you guys pointed out. I've been teaching this, nobody pointed out. Well, so here is a scenario. You have an ethylene. So, this part is what is going to absorb the light. You have the sigma bonds in this portion. You have pi bonds in this portion. So, this is going to preferably absorb because it's associated with the lower energy transition, and its absorption is at 184. The next example that you see has two double bonds, and they are separated by a chain of sigma bonds. So, that's kind of an insulation between these two double bonds. Now, if you shine in light onto this molecule, the position which it absorbs is not going to change, right? Still at 185 or so. Molar extinction coefficient is doubled now, because there are two of such units contributing to a intensity that is a double exact. Okay, so this gives you an indication as to how many number of such absorbing units are present in a molecule. If you have an idea about one particular unit, right, and you are given a molecule comprising multiple such absorbing units, you should be estimating the molar absorption coefficient in order to know how many of such units present in this molecule. So, it gives you an idea. So, two absorbing units directly gives you information with the molar extinction coefficient. Position does not change. When does the position change? If you connect them by a single bond. What are you bringing in now? One sigma bond separating two double bonds. So, what are you bringing in now? What do you call this scenario? One double bond placed alternately. Conjugation. Good. So, conjugation is the terminology you bring in here. When do you call a particular unit is conjugated? Alternate single and double bonds. What does it bring into the molecule? Stabilization. How does it get stabilized? Huh? Hyperconjugation doesn't come here. Resonance. Resonance is a concept that you bring in. So, that gives you extra stability to the molecule, right? It adds few pennies into the pocket, right? So, similar way, molecule gains some benefit due to conjugation and resonance. So, conjugation influences the absorption maximum. Okay, good. There's a good correlation between these two. Units are separated, there is no conjugation. You bring them together and effect the conjugation, the absorption is shifting now to what? 185 to 217, moving towards a lower energy region. Can we say that? Which means longer wavelength, right? Lower energy, higher wavelength, lower energy. So it is moving. Now I start adding 3 double bonds in conjugation. It is, instead of butadiene, now it is a hexatriene molecule. What happens there? It's further stabilizing. So that is affected in the energy level, separation between them, the lower energy and the higher energy. It is lowered down, stabilized, and you are shifting it roughly about, say, 30 nanometers or so, a big 30, 40 nanometers or so. There's a big jump in the wavelength shift. Okay. So molar extinction coefficient also increases, but you cannot correlate it in a way that you did it here, right? Because that's more or less increasing for sure, but not exactly as a multiples. Doesn't happen like that. Yeah.
Sir, so you take 135 hexatriene, and then if you connect it to make benzene, will the aromatic character of benzene further redshift it, or will it just follow with the pattern? Which is
What do you guess?
Should further.
It should, right? It should, right? So if you add more conjugating units to it, it's going to further shift the absorption, and electronic transitions can occur even with the lower energy, because the separation between the sigma star, pi star, right? Mainly pi star decreases, right? So, and hence you will be able to see color. This is the colored molecule. You know that. Beta carotene, initial slide I showed you, the orange color is because of its absorption in the visible region, and you are seeing a visible region absorption of 465 nanometers for beta carotene. How many number of double bonds you want to add to it? Can you count? There are about 11 double bonds in this molecule in conjugation. So to bring the absorption from ethylene to butadiene to hexatriene, all of them were in the ultraviolet region. If you want to bring it to visible region, then you need to add in roughly about 10 to 11 double bonds in conjugation. Only then you can push the absorption to visible region. Then compound becomes colored, you are able to see the color of carotene and you can appreciate the color. Right? Yeah.
Sir, what is a chromophore?
Chromophore is the light absorbing species, like pi bonds are chromophores. Carbonyls, right? These are chromophores. And there are, excuse me? Yeah, any light absorbing units. For example, arene he said, benzene he said. Benzene is a chromophore, right? Because it has double bonds in conjugation, delocalization is possible. It is a chromophore. Olefin is a chromophore. CC double bonds are chromophores. Carbonyl compounds are chromophores because they are light absorbing units. Okay, and there are some groups which can enhance the absorption properties. Those are attached often to chromophores. There is a basic skeleton which you define it as chromophore. You can add a few substituents to it so that its property is magnified. Those are called oxochromes. Those are called oxochromes, which can boost the absorption characteristics. Yeah. So those are called oxochromes. So there are which are often used to tune the absorption characteristics of a molecule. Okay. So this is a quick summary. As he said, benzene has an absorption at 253 nanometers. Okay. Again, you will notice a pi to pi star transition associated for benzene. Right. Now you fuse two benzenes together. What do you call this compound as? Naphthalene. They are also resonance stabilized. You can write canonical structures for these compounds, and you will see that the absorption has now shifted to close to 280 nanometers. So starting from benzene 253, you extend the conjugation, absorption shifts towards red, right? Go to naphthalene, to anthracene to, what do you call that? Not phenanthrene. Phenanthrene is an angularly fused tricyclic system for anthracene. Anthracene is a linearly fused. Phenanthrene is angularly fused. So if you add a benzene, not this way, but you attach it here, then that is angularly fused. That molecule is phenanthrene. Linearly fused ones are called anthracenes, right? If you add one more, it is called tetracene. Okay, tetracene. So this absorption is stepping into the visible region. Now this becomes orange color. Anthracene is colorless. Okay, this compound becomes orange color. If you add one more benzene to it, how do you call that as? After tetracene, it is pentacene, and pentacene is blue colored. Its absorption is at 580 to 600 nanometers. Okay, so you can see every annulation of benzene shifts the maximum roughly to about 100 nanometers. So you take benzene, attach all these hexatriene, whatever, you are certainly going to shift the absorption spectrum. Why does this property arise? How does this property arise? Basically, you are bringing in the occupied and the vacant orbitals energy closer to each other. You are lowering down, so on. So the transition would require a lower energy. That means it absorbs at a longer wavelength. Okay. So that gives you such a colored species. So fine, this definition I tested you, but you already answered, so I don't want to spend time on this. And these structures are okay, right? We talked about beta carotene. One of the important compounds in our eyes is retinal, right? Retinol to retinal transformation. It undergoes a simple cis-2 trans isomerization in our eyes that senses the brain, and you are able to detect the object in front of you. So vision chemistry is completely different. So then comes carotene, 11 double bonds, gives orange color. That is an yellow colored compound. This is an orange colored compound. You can also think of modifying the aromatic skeleton, such as benzene, by attaching some substituents simply to it. That is the example that is shown here. Okay, you have an amine functionality. You also have a nitro group. Amine by character can exhibit what? Mesomeric effect by resonance. So which means that is a donating substituent. It can give its electrons, gets engaged into resonance into the benzene, which is possible for the amine group. And nitro group is positionally suitable here. It is placed very, very suitably, so that you move the electron starting from nitrogen, it will reach the nitro group very correctly. So you are creating a charge separation within the molecule. That enhances the absorption property. Okay, because this mesomeric effect by resonance shifts the absorption to a lower energy region. This simple compound, benzene, is colorless, right? Because it has absorption of 253, ultraviolet region, no color. This compound is deep yellow colored compound. So by adding these oxochrome substituents, you can manipulate the absorption property of a chromophore. Right? NO2, amine, all of them are oxochromes. Any substituents you add to a chromophore to modify or enhance the absorption properties, you can do. Yeah. Nitro group takes up the electron density from the amine. Amine is supplying the electrons. It's a donor, that's kind of an acceptor for you. Or you may call it in your textbook terms, this is donating group and that is a withdrawing group and so on. Right? So all of that you can say. So this is another dye system. Again, you will see a same scenario here. Here amine is there. On the other end, you have the amine made positive. Right? Charge separation. Electrons can be drained out from the donor or the electron donating group side. Electrons can move through these bonds. It can reach this positively charged nitrogen. Always keep in mind from an electron rich source. Right? electrons would be migrating to an electron poor source. Or you would call it as from source to the sink. Always. Electron movements are like that. If you are writing a mechanism for any of the organic reactions, you should be very, very careful not to move your arrow from positive charge to a negative one. That is wrong. Okay? You should always look for moving arrows from an electron rich site to an electron poor site, or you may want to call it a source to the sink. Okay? So that's how electron movements happen. Here such systems, yeah, sorry. Because that establishes a resonance stabilized structure. It establishes a conjugated structure. It is more stable, and the gap between the occupied and unoccupied, or the filled and the vacant, gets closer and closer. Okay. Even from a small system, this is a popular dye, very strongly colored dye. So you can generate such systems even with a simple aromatic system. So you don't need to keep adding 11 double bonds to get to orange color. Not necessary. Okay. So that's where molecular engineering comes into picture. Well, so we talked about benzene. All of you know benzene is aromatic, right? What are the conditions for aromaticity? Anyone please. Huckel's rule is correct. What is that rule? What should be the condition? Planarity. I hear many planar.
It should have 4n plus 2 pi electrons.
It should obey 4n plus 2 pi electrons. If it is not 4n plus 2, it is anti-aromatic or non-aromatic. Okay. How do you decide between anti-aromatic and non-aromatic? For anti-aromatic, conjugated and 4n pi electrons. And for non-aromatic, the only difference is it should not be conjugated. What he says is correct. Okay. So for aromatic compounds, it has to be planar. It has to have a cyclic pi conjugation. It's very important. It has to have a cyclic pi conjugation. Okay. If you don't have a cyclic pi conjugation, then you can connect between hexatriene and benzene. Benzene also has 3 pi bonds. Hexatriene also has 3 pi bonds. Hexatriene is acyclic. It is not cyclic. Benzene is cyclic. Right? And we call benzene only as aromatic, not cyclohexatriene. Right? So it has to have conjugation, important, but more important is should have a cyclic pi conjugation. So when I say cyclic pi conjugation and planarity, what does it mean? These p orbitals are like this. Right? They are establishing a overlap between themselves. Right? You can allow them to deviate. How much these p orbitals should deviate in order to break the conjugation. Conjugation is scenario like this, right? Lateral overlap of p orbitals. Up to how much it will be establishing the conjugation? Up to 19 or 90, correct? Right? If you want to twist these orbitals, when it is completely orthogonal to each other, they cannot establish a lateral overlap of p orbitals. That's when you break the pi conjugation. Okay? So to some extent, if they are here, you can see, they are not now 0, but they are like this. Still they will be able to establish a conjugation. So deviation from planarity to some extent is allowed, as long as it can have cyclic array of p orbitals establishing a pi conjugation. But when it breaks, that falls into a category of non-aromatic compounds. Okay? So this is the summary. Now such kind of aromatic molecules, right, if you look at the aromatic stability, huge for benzene. 152 kilojoules per mole for benzene. That means what? It's very difficult for you to destroy the aromaticity within the ring. You would have studied that benzene it does not undergo any addition reactions. It only undergoes substitution reactions. Right? That is its innate behavior. So now you can't destroy the aromaticity of benzene. I'm not saying you cannot, you can, but it is requiring very high energy of 152 kilojoule per mole. What happens in the case of heterocyclic compounds? Such as, have you come across these compounds? So this is labeled as thiophene, this is furan, you would have had a nitrogen analog of this, pyridine, pyrroles, right? So all of these compounds you would have come across. They have relatively lower aromatic stabilization energy than that of benzene. Gives you a flexibility to disrupt the aromaticity quite readily than when you do so for a benzene. Okay, because their aromatic stabilization energies are 121 and 88. That means they are, it's lesser aromatic than benzene because they are heterocyclic. Okay, and you can see the difference in the aromatic stabilization energy or the lowering trend of aromaticity correlates with the electronegativity associated with the atoms that are involved in the heteroaromatic compounds. Okay, so first comes benzene. Then when you look at the heteroaromatic series, you will talk about sulfur, nitrogen, oxygen. So all of that comes. So it has lower aromatic stabilization. I am not going to say anything extra. These compounds are also aromatic, right? But it has lesser aromatic stabilization energy, gives you a flexibility to disrupt the aromaticity quite easily. So easy to do any reactions on it. Okay, now only we are getting into the topic. Okay, so these kind of systems could be very readily used for photo switches, light based molecular switches, right? So in a typical scenario, whatever we are going to talk about today is about the color change. So the color change between from a colorless state to a colored state and then back to a colorless state, right? A reversible process is called as photochromism, right? So chromism meaning color changes, photo light mediated. So light mediated color changes is what we are going to talk about. So definition wise, it's a reversible photo induced transformation at least in one direction, okay? Either from a colorless state to a colored state or from a colored state to a colorless state, then back to a colored state. So, of a chemical species between two different states having distinct absorption spectra. What it means when I say distinct absorption spectra, you should correlate it to the colorless state to a colored state. You know, colorless state means it absorbs in an ultraviolet region, that means less than 400 nanometers, right? When I say colored state is generated, their absorption spectrum will have a new evolution of absorption in the visible region. So you will have very distinctly different absorption spectra. So when a colorless state changes to colored state, you see this new peak that's appearing with a simultaneous decrease of this band, indicating that the colorless compound is only getting transformed to a colored state. Okay, so this changes you would notice. You can say this as a simple definition: species A gets transformed to species B upon irradiation with light. Species B can come back to A either by using a different wavelength of light in which the new species is absorbing, or you just switch off the light, allow it to acquire the thermal energy from the environment, then by acquiring the thermal energy to come back to the colorless state back. From B to A it can come. Yeah.
So does it necessarily only have to be from colorless to colored and color to colorless, or can it be between colors?
It can be between colors. It can be between colors too. But the difference should be very distinct. Otherwise, you will not be able to notice the changes very precisely. When they are distinctly different is fine. Okay. right? So, other than color, what all the things that can change with a molecule, right? It can undergo structural changes, and of course it should. That's what is represented in the form of color. So you will have structural changes associated. Because the structure undergoes a change, you can have some characteristic physical properties also undergoing change, such as dielectric constant could change, refractive index of the medium could change. All of this could be different for a species that is newly created. Okay, so all this could be monitored as well. You can monitor them as well. Along with the absorption, you can also monitor those property changes as well.
So if light is incident on this particular compound, you have a change in color. So how will you even detect the original color? If you cannot, how will you detect the original color?
The original color could be, you can record an absorption spectrum of it. You can record it in a very short time frame of say 1 second. It is not a continuous radiation, right? Be a pulse radiation. Record the absorption spectrum of it. Then put the sample to a continuous radiation. Now color is acquired, right? You can also induce multiple pulses to make more of the light in contact with the sample. So many of the, you can give multiple pulses. Then you will see slowly the population of the new species that is generated in the medium, for which you will see an evolution of the new absorption spectrum. Okay, it is possible. So the time frame, kinetics could be modified from a colorless state to a colored state. You can engineer them. You can record conveniently absorption spectrum for species A before irradiation. You can also record absorption spectrum for the species B, that is after irradiation. Both of them can be done. Okay. So applications are many. What we will be talking about is the photonic switches, some applications to photochromic lenses that we have on our glasses, right? Such kind of molecules are present in ophthalmic lenses. So when you go out from your house exposed to sunlight, automatically the glass changes. When you step into your house again, it becomes colorless, right? So the efficiency of the reversibility is very, very crucial for these compounds. It should not fade away with time. Besides that, you have other applications. This is a fancy item which I wanted to show, and I like showing it. And this is a photochromic paint that is coated on the building, okay, in Italy. What you see is sun rises this side. So it falls onto this side of the building, and the color of the building completely changes. Color of the building completely changes. It's a fancy application. And then when the sun sets on the other side, this part is lit now, and you will see that part is changing its color. And photochromic cars, photochromic t-shirts, all of them are in sale now, I think, right? Kids love wearing it because initially it is colorless. When they go in sunlight, some doll comes and they are happy. So similarly, a lot of fancy applications are coming from this photochromic molecules. Similar. You have seen it? I have not seen it. I have not seen it. Yeah. Yeah. Same color? Yes. When sun sets, it comes back to the same color. When the sun shifts to this side also, you will see this original color of the building. You can see right now, this part is changed color, whereas this doesn't. Okay, it comes back to the natural color. Okay. So now give us brief introduction of photochromism. Yeah.
Sir, is it 100% efficient, or would the color degrade over time?
It should be in principle 100%.
Okay.
Fading should be 100%. Acquiring color is a process. Moment it acquires color, it should fade back to 100%. Otherwise, application wise, you will have less feasibility. For example, in the ophthalmic lenses case, you can understand easily, right? If a color is generated, and if it takes a long time to fade back to the colorless state, you won't feel good, right? The reversibility of this process with which this backward and the forward process occurs should be very, very efficient. So that's why a lot of research work is happening in this area, particularly to make the absorption zero of the B species that is generated after photo irradiation in the reverse process. Okay? So that's very, very important. It's not a new phenomenon. Yeah, somebody.
If we ionize the compound, will it lose its photochromatic properties?
If you ionize this compound.
Yeah. If we ionize it, like there are no electrons that like go like transition. Like it'll be
You want to have a reversibility. If you
No.
ionize it, you have removed an electron from there already.
Sorry, sir.
You have to get back the electron. So excitation is the appropriate process.
Yeah, but in case like if it undergoes ionization, there won't be electrons to like undergo the transition, like come back to the ground state. So will it lose its
No,
property?
ionization means you're taking away an electron.
Yeah.
You're not bringing it back.
Yes, sir.
But in the excitation process, it gets excited.
Yeah.
And then the electron relaxes back to the ground state.
Yes, sir.
Right. So it is a reversible process.
Hmm.
This should be reversible. So excitation should be appropriate, not ionization.
No, sir. I'm not asking if it's appropriate. I'm asking if it happens, will it lose its property itself? Like
Yeah, obviously.
yeah.
It should.
Alright.
It will be a completely different story then. You can do that by redox means. Like we are talking about photochromism by light, where electrons are retained with the molecule all the time. People also use the electrochemistry. Right? That is called electrochromism. So you remove an electron from a molecule because that goes to the electrode, create a charged species with one electron, call it as a radical cation. Now the color of the solution completely changes. From the other electrode, the electron is injected back into the solution and it gets back the electron and then comes back to the natural state. So it is electrochemistry mediated. What you are saying is an ionization process. Removal of an electron, putting an electron back. So oxidation, reduction. Both of them are happening. And that's an electrochromism process. It is possible. But not in this case. If you remove the electron from here and then do photochemistry, it's going to be completely different. Yeah. It is used as an indicator.
Like if the pH changes, the color changes. So like
These options are coupled. You can do the process first with light, then change the pH and do some other process to generate a different color. Basify it, get the process back. From here you apply light, you do it. So it is a gated process actually. You can do that. You can do that. Actually people are correlating this phenomena like 0 to 1 in the computers, right? So like logic gates kind of stuff. So they do with light, with some other ingredient, chemical ingredient into it, operate a different process, then a different process. So many of such processes are coupled into one system. So you design a molecule like that. In principle, it is possible. Yeah. So history is dated back to 1867. Okay, very, very old history. Initially, there was not much of an understanding. I wouldn't go line by line and describe the story of it because of paucity of time. But what we will do is, in the beginning, what you should know is several of such phenomena were noticed. And they had a habit of writing. They were recorded. Okay. And they thought it is a color change. Some cases they were reversible, some cases they were not. But they could observe a color change from A to B. Okay. And those were all recorded. And now we realize that those processes they were noted cannot be called as photochromism. Okay. Because some of them showed reversibility, some of them do not show reversibility, some of them become reversible at very high temperatures and so on. Now we understand the phenomena of all of that, what is happening. So initially there was not much of understanding. Only after 1950s, right, where Hirschberg and Fischer coined the name photochromism, this area became very popular. And from 1960 onwards, 1960, 70s, 80s and all, we have a lot of instrumentation techniques evolved. Advanced level characterization came up. Spectroscopy techniques have evolved, right? So with those things, it was very easy to study such kind of a phenomena. And now you have ultra fast processes, you can even look at, in femtoseconds what happens to these molecules, right? So such development has happened. So along with the development, this field has also grown drastically, right? So because of the better understanding that has evolved. So various sets for your quick view. one such molecule is indolyl fulgides. They undergo reversible photochemical transformation from indolyl fulgide form to this form and then comes back to this form. Every substituents that you see on the molecule may be very complex to you, but what it means is they are engineered structures, optimized ones. Why do you have to have such substituents? If I start explaining, I have to tell so many stories, but we will take one particular system and then tell you. Okay, I'll summarize that. Another system that you are seeing here is oxazine. You find oxygen, you also find nitrogen in that skeleton. Okay, this is again reversible. In this process, what happens is the ring opens up, creates a zwitterionic species like positive and negatively charged intermediate. Switch off the light, it would come back to its natural state, which is colorless. What do you notice in this structure and this structure? What do you notice here and what do you notice here? Could you be able to find out? Ring is broken. So what it has resulted in? Charge separation. How can you see the backbone getting modified? How do you see the backbone getting modified? Initial structure versus the final structure. Huh? No? No, yeah, it is not cyclized, that's what he said. Ring opened. Okay, ring opened structures. It's just an electron movements along the backbone of the bonds. Okay, so it is a reversible transformation. So some electronic reorganization has happened. Nothing happens to the substituents. No atoms are lost, right? No atoms are made also, attached also. No atoms are lost, no atoms are attached also, right? So it is an atom economical process. You start with the starting material, some reorganization of electrons, new bonds are generated, and when you stop shining the light, bonds are broken, comes back to the natural state. So what I want you to see is the conjugation in this ring is limited to only this extent. Correct? This structure, if you look at, again it is retained within the benzene ring. There is no communication between these two partners. They don't talk to each other. When you shine light, when the ring opening happens, you see an extended pi conjugation that is established into the system. Do you see the difference? You can move these electrons all the way, push here, push here. It can be delocalized. It can be, you can write resonance stabilization structures for these structures. Right? So there is an extended conjugation that is established. What it means? You start from a less conjugated structure. Upon photolysis, you generate a more conjugated structure, which means you are switching the wavelength from a ultraviolet region to the visible region. That is what the structure design is all about. Okay. Every structure, if you look at, will give you this information. Okay. This structure also, because there is a spiro connection here, sp3 hybridized carbon is breaking the conjugation. Upon shining it with light, you establish a conjugation once again all along the backbone, right? And that color is noticeable. Again, in this system, two thiophene units are connected via ethylene, right? These substituents attached to thiophene, particularly these two substituents, will keep them away from planarity. So conjugation is to some extent disturbed. To begin with, they are less conjugated structures. When you shine light, they form CC bond. Because they establish CC bond, they have an extended pi conjugation. If you start moving the arrows from sulfur, you can take it till here. So an extended pi conjugated structure is established. So from a less conjugated structure to more conjugated structures. From a colorless state to a colored state, you can switch between. Okay. Every molecule is like this. Here also you have benzopyran. Now this is, the conjugation is limited only up to here. Right? From here, if you start moving the arrows, it would stop here. Now in the open structures, if you start moving the arrows from here, it would extend all the way, including the phenyls on the other side. Okay, they involve in extended pi conjugation. So the structure becomes colored. So this is how the engineering behind the molecules occur. This I discussed already. There should be a certain qualities for a molecule in order to exhibit a photochromic property. First of all, it should develop a color in order to be a promising photochromic compound. Control of color back to colorless state. When we say from color to colorless, I mean 100%, like he mentioned. It has to be completely fading away. It has to come back to colorless state. Sometimes it's good if you have a wide color range. What is the benefit? In ophthalmic lenses, when you have wide color range, what is the benefit? Huh? In a sense? Most of the, for ophthalmic lenses particularly, if it absorbs in majority of the color ranges, let us say, then it filters out as maximum wavelengths as possible, right? Because when the UV light, when you are exposed to sun, when the UV light hits your eye, it's all filtered by the material that is coated on here. And it does the process of ring opening, gives you the color. That means these lights are absorbed by the molecule and it never hits your eye. Okay? If it is absorbing majority of the portions, then maximum of the light is filtered, right, in that particular range, and your eyes are protected. So it is better to have a wide color range so that it can absorb most of the wavelengths, and for the application purpose, it is very good. And it should be having a long life, in a sense that number one, when the first cycle completes, right, colorless to color, then comes back to colorless state. You should be able to do this process without any decay of the sample multiple times, right? So you should have very long shelf life, which means many times it should be able to be, you should be able to use them without any decay, because many of the compounds, organic compounds or whatever, when we expose to sunlight, they would tend to degrade with the time. Such degradation will end up in loss of the material that is coated on the surface, right? That shouldn't be happening, and reversibility should be very quantitative every time. Okay? That one has to ensure. Colorless rest state. Rest state should be colorless for application. Okay? So always you start from colorless to color. That's what it means. So you have to rest state. In all these reactions, whatever I had shown, particularly you have seen a movement of electrons along the carbon backbone. Okay, you have a carbon backbone. Along that, you have the movement of electrons. Carbon-carbon bonds are established. These kind of reactions are called as electrocyclic reactions. Call them as electrocyclic reactions. Electrocyclic reactions come under the category of pericyclic reactions, where no atoms are lost and no atoms are created, but there is some electronic rearrangement that happens. Okay, so it is a reversible process anyway. So this here is an example that you see hexatriene. You subject it to heat, thermal conditions or probably light. It would cyclize to give you a carbon-carbon bond formation. What has happened here? One pi bond is lost. Are you able to notice? One sigma bond is created. So one sigma bond is created at the expense of a pi bond. Simple electronic reorganization has happened to this molecule. No hydrogens are lost, no carbons are lost. The skeleton is intact. Similarly, here is another example. Butadiene to cyclobutene. One of the olefins, pi bond, has been converted to a sigma bond. These reactions typically involve simple bonding electrons undergoing some reorganization. Okay, so such reactions are commonly used. What are these reactions often driven by? If you look at, they are driven by the molecular orbitals. Let us not develop the molecular orbitals now, then you may have to stay for the whole of the day. So to do that, you will find the carbon-carbon bond formation is facilitated by the overlap of the p orbitals, right? In the pi skeleton, what do you have here? these p orbitals, right? So this end will have a p orbital like this. This end will have a p orbital like this. And if these p orbitals, these two, okay, one side of the olefin has the same phase, then when they cyclize, it should form the bond. How do they cyclize? If you have to make them of the same phase overlapping each other, this is positive, let us say, wave signs. Now, if you want to form a bond, how will you move? Both the positives should come together, right? Both the positive phases should interact with each other. So, you would move like this. Positive, positive come together. What happens with negative, negative? Still it would form the bond. So, you would move like this, right? So, both the negative ends come together, form the bond. What happens if you have a scenario, the orbitals, the terminal orbitals have different signs? Positive, negative. How do you move the bonds? How do you move the orbitals? So, you would, this one is moving clockwise. This one should also be moving the same side. So, you will have the positive of this and the positive of this would be interacting, establishing the bond. This was proposed by Woodward and Hofmann, for which they got the Nobel Prize. Woodward and Hofmann. So, the pericyclic reactions, particularly the electrocyclic reactions that we are discussing about, is often connected to the orbital interaction. Okay? And this is dictated by the type of reaction that you are dealing with. You are going to do thermal conditions, or you are going to use light for accomplishing this reversibility. Okay. So, we are mostly talking about, so this is, if you move them in the same direction, you call them as conrotatory mode of operation. These are some terminology that were given by Woodward and Hofmann. If you are talking about opposite directions, you start to move in order to bring these two lobes interacting with each other, then you call them as a disrotatory mode of operation. Okay. So, ultimately, the molecule decides, depending on the conditions, whether it has to form a bond under a particular condition or not. And how it is dictated? Dictated by the signs of the lobes and the direction with which it is going to move. Right. So, these terminologies you should be familiarizing yourself. These are some examples. Stereochemistry also matters here. It works very beautifully in a planned manner. You can, based on the set of rules provided by Woodward and Hofmann, you can even decide a priori the course of the reaction. Okay. So, you start with this butadiene with the methyl substituents. Look at this alkene, it is trans. You are familiar about trans and cis? Okay. So, this is the trans geometry. This olefin is in trans geometry. This olefin is also in trans geometry. And if you take this as a starting material, okay, let me go to directly photochemical conditions. So, this is, methyl is again trans. Methyl is again trans. Now, if you look at the sign of the lobes, under photochemical conditions, to develop these molecular orbitals, the molecular orbitals would resemble that of the psi3 molecular orbitals. Okay. So, the sign of the lobes are positive on either sides. Now, if you have to form a bond, these two same sign of the lobes should meet with each other, right, to form a bonding interaction. If you have to establish a bonding interaction, then the movement of it should be like this and the movement of it should be like this. So, one is anti-clockwise, another one is clockwise, right. So, such a rotatory motion is called disrotatory motion, which will favor in bond formation. What if I rotate it on other direction? Say I am bringing the blue in, I am also moving it here, then I am bringing actually a red and blue to meet, which is not possible. It will create an anti-bonding scenario and hence bond formation is not possible. So, condition can dictate what kind of rotation mode that it is going to take in order to establish the bond. This is very, very important step that is used in the photochromism based molecules. So, first example that is shown here is benzene. I told you it is very difficult to destroy the aromaticity of benzene. So, you will not see any color because as such it does not undergo any reversibility. It does not have a reversible scenario. Okay. So, it is very, very rapid. Before you detect them, they would vanish because destroying them is not going to be very easy. So, then came to this scenario. People modified the benzene to thiophene, and we know the aromatic stabilization energy is quite low when compared to that of benzene. So one can disturb the aromaticity quite readily. If you take such kind of thiophene, right, dithionenyl ethenes, to thiophene substituted ethenes, and shine light onto it, you will see at 20 degrees itself, you will see the color, and that color is persistent for about 12 to 15 hours. Color you can store in the refrigerator, the same solution. Okay, they are stable. Slowly they will fade away, but still you will see the color there. Okay, so the half-life for this is this. When you don't have any substituents here, right? Okay, so I will stop here.